Right, welcome back. And so on Monday's lecture, we have introduced the recommender system, the content-based recommendation techniques, and also the collaborative filtering. So for collaborative filtering, we mainly focus on the user-user collaborative filtering or user-based CF. So the idea would be because we want to predict or estimate the rating of item I given by user X. Right. So user-based collaborative filtering, the idea is to find similar users to user X while all these users have the rating of item I. Then we can estimate the rating of item I based on the rating of item I from all these similar users. So this is the idea of user-based CF, and apparently another view of this problem is from item-wise. So this is item collaborative filtering. So the basic idea would be we use the similarity between items, right, instead of users, to make predictions. So for item I, we find other similar items, and we will define this similarity function later. But actually, we can reuse the similarity functions that we have introduced before. And then we estimate ratings for item I based on other ratings for similar items. So we can use same similarity metrics and prediction functions as in user-user model. So this is a prediction function where the Sij is the similarity of item I and j, and Rxj is the rating of user X, here should be X, on item j. And this Ni given X is the set of items rated by X that is similar to I. So if we use an example to illustrate this idea, it would be like, for example, I am the user, right? And the recommender system want to predict my rating of a shirt, for example. So what it gonna to do is that it's the recommender system trying to find similar items to shirt. For example, T-shirt. I'm just saying. I mean, or pants, or shoes, for example. So, but it will not count, for example, the books, right, as a similar item to a shirt, or a video game. It's different, or won't be considered as similar item to shirts. All right. So then, how to predict the rating of shirt is based on my rating of, for example, the shoes and T-shirts or pants. So based on these clothes. Now, if we look at this example, where we look for items that are similar to item 5, because what we want to predict is the rating of item 5 that is given by Alice. So we have Alice's rating for the items from 1 to 4, and we want to use these ratings to predict the rating for item 5. But shall we take shall we take the ratings of all the items here? Actually, no. We only want to take the ratings for those items that are similar to item 5. By similar, you can take the prediction vectors here and try to compute the similarity. And for example, from what we can observe, most likely item 1 and 4 will be considered as similar items to item 5. Then the prediction of this rating should be based on this 5 and this 4. Now let's look at this example, and we can do some computations. I will show you how to do this item-item collaborative filtering. So assume that these are the movies or the items, and these are the users. And for the white box or white cell, it is unknown ratings. And for the red cell, it is the rating between 1 to 5, like 1 star to 5 star. And what we want to do, we want to predict the value here in the red cell, which is the 5th user, the prediction of movie I from the 5th user. So the first thing we're going to do is we need to compute the similarity between movies or items and find those movies that is similar to movie 1. So here we use a adjust cosine similarity. It is just another way to compute the similarity. Well, here you can also use other similarity functions as well. So for this adjust cosine similarity, what we do is that we first subtract the mean rating from each movie I. For example, for the first movie, the mean rating would be, because the first movie has been rated by 5 users, right? So the mean rating would be 3.6. Then we subtract 3.6 from those movies has been rated. That's why we get. That's how we get this row 1. Right? We can do similar things for other rows. For example, let's try to do it for row 3. Then the mean rating would be the sum of this 8 cells, which is 24, divided by 8, which is 3. So the new row 3, if we write it here, would be -1, 1, -2, -1, 0, 1, 0, 2. And for other parts, we just put a 0 here. Then we compute the cosine similarity between rows. Here is what we have. Here's what we have. Then apparently movie 3 and movie 6 are considered similar movies to movie 1, which where we will use the ratings of movie 3 and movie 6 by user 5 to compute the similarity weights. So given the similarity between movie 1 and 3 is 0.41 and 0.59 for similarity between 1 and 6, we can compute the value here, which where we use the function that has been introduced before. So it is a weighted average of the similar movies rated by the same user. So if we compute it like this, we would get 2.6 as the final result. One interesting observation is that in practice, if we compare the item-item collaborative filtering and user-user collaborative filtering, in practice, it has been observed that item-item often works better than user. The reason behind this is that the items are similar. The items are simpler, but the users usually have multiple tastes. What does it mean is that, for example, two users, they may have a similar taste on food, for example, but they have totally different tastes on dressing. Right? Just an example here. And however, for items, given two items that are similar to each other, the users, for a single user, for a specific user, he or she should have a similar taste on similar items. So that is one possible reason behind this observation. And now let's discuss a little bit more about ratings. So for explicit ratings, it is probably the most precise ratings and most commonly used. For example, using like in many, for example, in Apple Store or in bookings, we're usually required to give the application or give the hotel with a score or with a star. To assign stars to an item from 1 to 5. So it is most commonly used way, but the main problem is that users are not always willing to rate many items. So in this case, the number of valuable ratings could be too small, and the sparse rating, which will lead to a sparse rating matrix, hence the poor recommendation quality, because the estimation of the, for example, in the example before, consider it the matrix getting more sparse, then when we compute the similarity between the items, it could get more inaccurate. So the problem here is how to stimulate users to rate more items. On the other hand, for implicit ratings, right, which is typically collected by the web shop or applications in which the recommender system is embedded in. Right? So when a customer, for example, buys an item, then many recommender systems will interpret this behavior as a positive rating of that item, or the clicks or page views or the time spent on some page or the demo downloads. All this can be considered as positive ratings. Implicit ratings can be collected constantly and do not require additional efforts from the user side. But the problem is that one cannot be sure whether the user behavior is correctly interpreted. For example, a user might not like all the books he or she has bought, or the user also might have bought the book for someone else. So in this case, the ratings based on the user behavior is not correctly interpreted. Also, if we consider this kind of implicit ratings, it cannot be like have multiple levels like implicit ratings from 1 star to 5 star, for example, because it can only or usually be interpreted as a positive rating, or actually you don't have a negative rating in most cases, right? And also for even for for a positive rating, you don't know whether the user likes it very much or just buy it for some other reasons. And sometimes we can use implicit ratings in addition to explicit ones to enhance or in order to obtain more ratings for the recommender system to do the prediction. So if we consider the complexity of collaborative filtering, the most expensive step is to find k most similar customers or k most similar items. So the time complexity here would be big O of x. So x is the size of all the customers, right? The number of customers or items depends on what kind of collaborative filtering you are using. So it is too expensive to do that at runtime. So if we consider to pre-compute this kind of similarities, the naive pre-computation also takes time of big O of k times x. Sorry, my mistake. Here should be the size of x to the power of 2 has nothing to do with k, because essentially we need to compute the pairwise similarity between all the customers or all the items. And if we consider advanced algorithms to do the pre-computation, for example, we can use near neighbor search in high dimensions as LSH we have introduced before, or some clustering algorithms. So we can cluster similar items or customers together in one cluster, or using some dimensionality reduction techniques to reduce the computation cost. And also this kind of operations is supported by Hadoop. So we have Apache Mahout, which can be used to do the computation using its embedded algorithms. So if you still remember in Monday's lecture when we discussed the key problems in recommender systems, there are 3 key problems. One is to gather the known ratings for the metrics or obtain the ratings, right? And the second is to predict the unknown ratings from the known ones, which we have introduced different methods like content-based recommender systems or collaborative filtering. So the third one would be the evaluation. So what is a good recommendation in practice? What is a good recommendation system? So we firstly consider in practice what is a good recommendation. So basically in practice, the evaluation is based on the user's feedback. Although the user's feedback may not be that explicitly existing, right? But we can somehow make a good guess based on the user's behavior. For example, by using the recommender system, if we observed the total sales number increased, right, then we should consider it a good recommendation. Also, other signals including like promotion of certain items or click-through rates or interactivity on platform, or customer return rates or customer satisfaction and loyalty. So all these signals or factors can be used to judge whether it is a good recommendation or it is a good recommendation system in practice. But when we design a recommended system algorithm, or when we implement a recommender system, before put it online, we need to evaluate our implementations as well. So in this case, the commonly used way is to reserve a part of the data for testing. For example, assume this is all the ratings that we've obtained so far. Although it looks very it looks small because it is just an example here. So what we're going to do, we're going to reserve a certain part of the rating matrix, and we mask the ratings to using a question mark, so you won't be able to see it. The model won't be able to see it, and you use this as test dataset. Although you do have the real ratings here, so when you use your algorithm to do the prediction, you can compare it with the ground truth, right, to judge whether the recommendation you've made is good or not. Well, the measurements of evaluation. Right. So there are several ways to measure whether the goodness or the effectiveness of the recommender systems. So if we put them into two main categories, it is based on the returned the return value of the recommender systems. So the first type, which is also what we have been discussed in this course, is so the recommender system will return the rating of a specific item by a specific user. So under this scenario, the most commonly used evaluation measure is the RMSE, so root mean square error. The formula of RMSE is like this. So essentially, it is the square root of the sum of the square of the difference between predicted rating and the true rating. So since we have masked the testing data, so we do have the true ratings. And this is the most commonly used measurements. But we can also use others. For example, the precision at top 10. Here actually you can adjust this 10, turn it into other numbers like 5 or 20. So the idea here is that because we have for a given user, we have predict his rating of different items. Although we do them one by one, but we do have the ratings for different items. And if we sort the items, we sort the ratings of the items, then we can obtain the top 10 items with highest ratings. Assume they are, say, item 1 to item 10. This is the predicted items with highest rating. And let's also assume that I1 to I10 is the ground truth, like the true rating. The 10 items with the highest true ratings. If we define this as the predicted S and this is the S, so the precision at top 10 would be the size of the intersection of the predicted S and the true S divided by 10. So it's like how many items that in S has been correctly returned in the predicted S. Also, the rank correlation. So here we use Spearman's correlation between systems and users' complete rankings. Right? And for another type of the recommended systems, so those who only return a 0 or 1, so we also call it a 0-1 model. So basically, the recommended system will give a binary answer, say whether it should be recommended or not. So 0 represents should not be recommended, and 1 represents should be recommended. So if we consider this scenario, there are also some measurements that can be used to evaluate the predictions. For example, the coverage, which is the number of items or users for which a system can make predictions. Or precision, which is the accuracy of predictions. It is similar to the precisions at top 10 here. Or the ROC curve, which is a trade-off curve between false positives and false negatives. So we're not going to dive into the details of these measurements, but if you are interested, you can do your own research, search online. These are just very common topics. Now let's have a look at the winner of the Netflix prize, which is a competition of recommended systems. So let's have a look at the winner of that competition, like how its recommendation system works. So just a few statistics about the Netflix prize. So the training data would be 1 million ratings, which comes from 80,000 users and nearly 18,000 movies. The data is collected in 6 years, from 2000 to 2005, and the test data is the last few ratings of each user. So we actually got 2.8 million ratings as test data, and the evaluation criteria is the IMSE, which we have introduced before. So here we actually need to divide it by R here, because we're considering the mean, but since this R usually is the same, so it can be ignored as well. But here, so the formula is just essentially the same as we have introduced before, right? And the baseline of this computation, which is the IMSE of the Netflix system, is 0.95. So it is not too bad, but it is not good enough as well. Here, just remember the IMSE, because it is an error, so it should be it is definitely always larger or equals to 0, and the less IMSE is, the better the recommended system is. Right? So we do expect a smaller IMSE. And for the competition, they actually have 2,700 plus teams, because there is a 1 million prize for if you can get a 10% improvement on Netflix, you will get this prize. So basically, here is the what the metrics the metrics looks like. We have users and movies, and the ratings. So the ratings is between 0 and 5, so integers. integers between 0 and 5. 1 and 5. And we have a test data set. Well, the figure here is not very accurate, but just trying to give you the idea that part of the matrix is reserved as the test data set, because the real way of generate test data is to use the last few ratings of each user, right? So the IMSE is the evaluation criteria, and so this is the true rating of the user X on item I, which is RXI, and this is the predicted rating of user X on item I. So for example, R36 is the true rating of the user 3. So yeah, so R36 should be a user 3 on item 6. Yeah, here this one should actually be R63. So it's user 6, user 6 on item 3. And the winner of this Netflix competition, it actually uses multi-scale modeling of the data. So the solution of the winner is actually a combination of several levels, or 3 levels to be specific. So the first level, which is a global effects, which we will introduce these levels one by one later. And the second level is a factorization level, which is trying to model the regional effects of the data. And the last level is a collaborative filtering level, which extract local patterns, or to have a refined local view of the data. So basically, we have already introduced the collaborative filtering in this course, but we need to discuss the global effects and the factorization. So that's before we introduce them. Here is the performance of the various methods. The winner actually achieves a IMSE of 0.85, and the Netflix baseline is 0.95. So if we use a global average, which means instead of we do the prediction, we just sum all the ratings and do the average, and use the average as the prediction. If we do that, the IMSE would be this large. And if we do the average on different users, we will have the IMSE like this. And if we do the average over movies, this is the number. If we use a basic collaborative filtering algorithm, this is what we can have. And if we use CF plus bias and plus learned weights, which you would see what they are, then we would have a better one, but not the best. So the best actually makes use of global efforts, factorization, and collaborative filtering. So let's start from the global effects. So the idea of global effects, let's use an example here. For example, if the mean movie rating is 3.7 stars, let's see, and given a movie, for example, the Sixth Sense, say it is 0.5 stars above the average, right? And if we also know the user, which is who is Joe, Joe rates 0.2 stars below the average, right? So we can make our guess, right? The mean movie rating is 3.7, and the movie here is 0.5 above the average, and the user here usually rates 0.2 below the average. Right? So if we do the computation, we will get 4, right, as a baseline estimation. So Joe will rate this movie like 4 stars. Now say the local neighborhood, if we consider local neighborhood, CF is collaborative filtering and NN is near neighbors. So we know additional information like Joe didn't like a related movie, Science. Well, I don't know either of these movies, but let's say these 2 movies are related somehow. Maybe they share the same director or share the same actors. I don't know. But if we know that information, right? So this information is local because it's local neighborhood because this information is strictly linked to the specific user and the movie. Right? So if we know that Joe didn't like a related movie, so our guess is that he may not like this movie as well. Right? So we somehow do the final estimate, final estimation. Say Joe will rate this movie like 3.8 stars, which is even lower than 4 stars. Our baseline estimation based on global effects. And don't think global effects is not useful because, as you can see here, although these numbers are not very good, but also these numbers are not that bad, considering the ratings actually varies from 1 to 5. Right? So with this naive usage of global informations, we can still have relatively good estimation. Right? All we need to do is to further improve it. Now let's discuss how we implement this kind of idea in practice or mathematically. So basically, the idea is that we get better estimates if we model deviations. So this BXI, this is the predicted rating. So let's start from this BXI. So this BXI is the baseline estimation of RXI. Right? So BXI actually equals to mu plus BX plus BI. So the idea is illustrated here. Right? So here, this one is BXI. Now, mu is the overall mean rating, right? The global mean of ratings. And BX is the rating deviation of user X, which is the average rating of user X minus mu. Right? And BI is the average rating of movie I minus mu. So it's a rating deviation of movie I. So the baseline estimate for RXI is the overall mean rating plus the rating deviations of user X and of movie I. So this is BXI. What we do here is try to revise BXI. So here the idea is consider the neighbor of item I for the same user. So these neighbors are, if we denoted them as J. So Sij is the similarity between item I and item J. Rxj is what we have, is the rating of user X on item J. And Bxj is the baseline estimate of Rxj. So by using this, we can model the deviations of item j, right? Item j with user x based on the baseline estimate. So this is an average one. By using this, we can have a better estimation. So essentially here the idea is what we have trying to illustrate here. And the problems or the issues of this idea is that first of all, the similarity here, the similarity measures are arbitrary. It does not have a rigorous definition, right? And also the second problem is that the pairwise similarities, because we consider the similarity between any item pairs I and j, the pairwise similarities neglect the interdependencies among users. Also, taking a weighted average can be restricting. So the solution would be, instead of using the similarity Sij, we use Wij that we estimate directly from data. So here we use a weighted sum rather than a weighted average. So the formula is rewritten as this. So it's just a sum of weighted sum. Sorry, it is just a weighted sum of the deviation of the ratings of user I, of user X and item J over the baseline estimation. So here NIX is the set of movies rated by user X that are similar to movie I. Wij is the interpolation weight. So it can be just some real number, and also does not matter whether the sum of Wij equals to 1 or not. So we do allow that the sum does not equal to 1. And Wij models the interaction between pairs of movies, and it does not depend on user X. And we will discuss how to compute this. Right. So the idea here is that we know that the predicted rating of Rxi is the baseline estimate plus the sum of the weighted sum of the derivation here. So we know we can compute Rxj, we can compute Bxj and Bxi. So the only thing that is unsure is this Wij. And also remember, the error metric is the IMSE, or equivalently SSE, which just we don't need to compute the mean and the square root. So the idea here is to find Wij that minimize SSE on training data, because we don't have the testing data. And hopefully, I mean, when it works on training data, works well on training data, it will works well on the testing data as well. And so essentially, by doing this, we are model the relationships between item I and its neighbor J. So Wij can be learned or estimated based on X, the user X, and all other users that rated I. Because we also need other users that rated I to estimate, to extract the relationships, or to model the relationships between item I and its neighbors. So the goal is to make good recommendations in order to quantify the goodness. We use IMSE, and lower IMSE means better recommendations. So what we want is that we want to make good recommendations on items that user has not yet seen, but we cannot directly do it. It is just the basic concept in machine learning. We have introduced it before, I believe. So what we are going to do, we're going to build a system such that it works well on known ratings or the training data, and hope the system will also predict well the unknown ratings, which are the test data. So the idea is what we're going to do is to set the values W such that they work well on the known user item ratings. In order to do that, just like all the machine learning tasks, we need to define an objective function and solve the optimization problem. It's like to solve the optimization problem in order to find the W that makes the objective function as small achieves its minimum value. So we need to find a wij that minimize SSE on training data. So this is the objective function. It is the sum over xi pairs in the training data, and what is to be summed is the square of the predicted rating. Sorry, the square of the difference between predicted rating and the true rating. True rating we can get it directly, and predicted rating can be estimated as this. So we have the baseline estimation, and we have the weighted sum of the deviations. So the only variable here is wij. It's wij. So here we actually think of W as a vector of numbers, or it is in fact a matrix of numbers. Right? So it can model the the relationship between items I and item j. So far, so we have the prediction of or the estimation of Rxi. We have derived the weights wij based on their role, and there's no use of an arbitrary similarity measure, right? And they it explicitly account for the interrelationships among the neighboring movies. So we will have a break here, and then we come back and discuss the latent factor model, or the factorization part layer in this model, or in this method.